Okay, in today's lesson, we are looking at the sign of the second derivative. You need to listen very carefully. You know how you start off with a curve y equals some function of x. Y is some function of x. It could be x squared plus 3x minus 2 or something. When you do dy dx, that's the rate of change of y with respect to x. Now, if I write WRT, it's with respect to x. So if I've got y as some function of x, it could be x cubed minus 2x plus 3x minus 5, right? Dy dx is the rate of change. That's how you look at it, the rate of change of y with respect to x. Now, if we look at d squared y by dx squared, it's the rate of change of dy dx with respect to x. That's what the second derivative is. It's how is the gradient changing. So dy dx is how is y changing with respect to x. D squared y by dx squared, which is the second derivative, is another rate, but it's doing the rate of the gradient. How is the gradient changing? Okay? So it'll say, and it'll tell you things like the gradient's getting steeper or the gradient's getting flatter. All right? That's what it'll tell you. So it's the rate of change of the gradient with respect to x. Now, if the second derivative, d squared y by dx squared, is positive, you know how that means? That means that the rate of change of the gradient is positive. It means that the gradient is increasing if the second derivative is positive. The gradient is getting steeper. The second the value of dy dx is getting bigger. Now, if it's a positive number, it would be getting steeper. If it's a negative gradient, you tell me about, if this is a negative gradient, couldn't that be -5? For example, it's quite steep. This might be -3 gradient, that might be -2 gradient, that might be -1 gradient. See how the numbers from -5, gradient of -5 to a gradient of, say, -1, the gradients, the numbers are getting bigger. -1 is bigger than -5. Here, the gradient might be a half, the gradient's 1, the gradient's 2, the gradient's 5. See how the gradient's getting bigger? Now, okay, so, look, for this whole bit then, look, I might say this is a large, just watch here. Do you think that's a large negative gradient? It's quite steep, isn't it? Watching. That's a smaller, these are all negative gradients, but they're getting smaller. Can you see my big negative means that might be -10, that might be -5, that might be -2, these might be -1 gradient. The values are getting less negative, which means that the dy dx is increasing. The value of the gradient is increasing. -5 to -1, or -1/2, or -1/4, or whatever. It's close to 0 down there. Gradient here now is 0 at the end. Now, look at this. This is a positive gradient, but it's quite small. And this is a big positive gradient. Wouldn't you say that's steeper? I'd say that the gradient's getting bigger here too. Small positive number, big positive number. Big positive number, big plus. Dy dx is getting bigger. Dy dx is increasing. That's why the second, now if dy dx is increasing, the second derivative is positive, because that's the rate of change of dy dx. Here, dy dx is increasing here as well, because I'm going from like big negative values to smaller negative values. And the smaller negative values are bigger numbers than the bigger negative values. Now watch here, big negative, very negative. Less negative, 0 there. Small positive gradient, very big positive gradient. So all the way along here, I'm going to make up numbers. -8, -5, -3, -2, -1. Gradient's -1/2. Here gradient's 1/2, 1, 2, 5, 10, whatever. See how the numbers just kept getting bigger? Now look at that. That's what we call concave up. So if the second derivative is positive, concave up, smiley face. So this is what we say. If the second derivative is positive, we have concave up. Actually, what can you see down here? That's a minimum or a maximum of the graph. Yeah, so each of these is concave up, and at the very bottom, see, if you're going from negative, let's say I've got a number line, you're going from negative numbers to the positive numbers, don't you have to pass through 0? Guess what? Right there is 0. That's 0 gradient. All right, but all here, this is all concave up. All right. Now, let's look at the same thing here. Let's say, all right, would you say this is a positive or a negative gradient? I'm doing tangent to curve. Small negative, do you think this is negative? Is it really steep negative? That's really steep negative. I'm just trying to get bigger, right? I'm making my negatives bigger as I go around, down. Small negative, bigger negatives. Looks like if you're going from -1 to -10, your number's getting smaller. All right, let's look at this one. Is this a positive gradient? Quite steep. Then the curve flattens. Very big positive gradient, then smaller as I go along. So that might be +10 to a half. Numbers are getting smaller. So the gradient is changing and the value of the gradient's getting smaller. That means, remember, the second derivative is the rate of the change of the gradient. dy dx is decreasing. It's getting smaller. See, dy dx is the gradient, and the gradient's getting smaller as you go along. The value of the gradient, if you were to calculate it, you get a smaller number. So what about this? It's called concave down. So because the gradient is changing and the gradient is getting smaller, we say that the second derivative, which is the rate of the change of the gradient, is negative. So therefore you've got a concave down curve. Now let's look at this graph here. That's definitely positive gradient and quite big. Smaller positive, very small positive. This will be 0 there. These are negative gradients, small negative, very steep negative gradients. So if I go from +10 down to 0 and then back down to -10 in terms of gradient numbers, haven't I just gone smaller all the way? Isn't my gradient just getting smaller? Okay, so if the second derivative is negative, concave down curve. Gives you the... Now, but sometimes the curve can be increasing or the curve can be decreasing. This is a decreasing curve. That's an increasing curve, but it's increasing at a decreasing rate. This is going up, but it's not going up as much anymore as you go along. This is going down. This is decreasing at an increasing rate. Oh, well, actually, no. We don't say at an increasing rate. The number's getting smaller, so as we go down, the gradient's getting smaller, even though it's steeper. If I'm talking about the number value of the gradient, -0.5, -1, -5, gradient's -10. All right. Now, these are all concave down curves. Now, a stationary point. So, you know what a stationary point is? What's a stationary point? When dy dx is 0. So a stationary point, remember in the last lesson, we were saying stationary points are when the gradient's 0. Now, when the gradient's 0, look here. If I just look at the curve, that's gradient 0 here. That's, you know, the tangent. Here, at the bottom here, dy dx is 0. But I know that, you know, this is concave up, so the second derivative is positive. I know I've got a minimum here. So at the very bottom there, that's called a minimum. At the very bottom, when dy dx is 0 and the second derivative is positive, and you've got it means that you've got concave up, upward concavity, concave up, and you've got a minimum. This is concave down, but I know at this point right there, this is the actual curve, that dy dx is 0 at that point. Here I've got a maximum. So we know that when, remember in the last lessons we were looking for stationary points, and stationary points are when dy dx is 0. So when dy dx is 0, I know I've got a stationary point. So if you've got dy dx 0 and the second derivative is negative, you've got a maximum. Okay, happening there. Just continuing from this sheet. Okay, from yesterday's, we were up to here. Now we've just gone through all of this just now on the other worksheet. A stationary point with downward, that's concave down, is a maximum. That's what we were just doing. So just said, sorry, and before, a stationary point that is concave up will be a minimum. A stationary point that's concave down will be a maximum. Remember, for a horizontal inflection point where the first derivative is 0, you'll get a concavity change around the stationary point. We were just doing this before. And a point where concavity changes is called a point of inflection. For points of inflection, the second derivative is 0 and the concavity changes about the point. So if the second derivative is 0 at the point where x is a, then a point of inflection will occur at x is a if the sign of the second derivative changes on either side. Remember, it's got to go from concave up to down or down to up. Otherwise, it's not an inflection. Just looking at this one question here, it says, given that the function of x is this, find the values of function of 3, f dash 3, f double dash 3. So we're just looking at the function at the point x is 3, and what can you say about the shape of the curve as it passes through x is 3? I'm not finding all the stationary points or anything. I'm just doing a little investigation. Let's just look at f dashed x. What's that? So we're going to look at f dashed x and f double dashed x. What have we got? 6x squared minus 18x plus 12. The second derivative is 12x minus 18. Now, let's look at what it was asking us to do. The function of 3, f dash 3, and f double dash 3. We're going to work these all out. Now, function of 3 means to substitute x is 3 into the original function. So that will be 2 times 3 cubed minus 9 times 3 squared plus 12 times 3 minus 2. What's that? 2 times 27, 54 minus 81 plus 36 minus 2 minus 83 plus 90. Is it 7? Now, what does that mean? That 3, actually you're going to tell me which point actually lies on the curve. What's f dashed 3? You put it into the f dashed x, we get 6 times 3 squared minus 18 times 3 plus 12, 6 times 9, 54 minus, isn't that 54 as well? Plus 12, is that right? 12. And f double dash 3, put it into the second derivative, 12 times 3 minus 18, isn't that 36 minus 18, which is 18. Now, okay, it says, let's think about it now. What can you say about the curve at the point x is 3? I'm going to sketch it. When x is 3, do you know the y value? You do, because function of 3 is the original curve. So when x is 3, y is 7. So I'm going to put the point 3, 7 up here. That's a definite. So I know that when x is 3, y is 7 on the curve. See, when you substitute into the function, that's the actual curve. Tell me about the gradient when x is 3. Is it steep? It's very steep. So, curve, so this is what I know. The curve passes through the point 3, 7. It has a steep positive gradient of 12, positive gradient. Why do we know that? Because f dashed x is greater than 0 at that point. And tell me about its concavity. And it is concave up, as the second derivative is also positive. So I've got to draw a positive curve that's going upwards. Do you get it? So is it going to go, well, I've got two options to do a positive curve. I can either go, well, that's a straight curve. That's not that. It's either going to look like this or look like that. They're all positive. Which one is it going to be? That's positive curve that's not changing its gradient. So the rate of change of this gradient, 0. Gradient's the same. Tell me about this gradient. Is it getting bigger? Positive, yeah. So, but this gradient's getting smaller. So the curve should look like the middle one at that point. So I'm just going to go, and let's actually, so that's what we think is happening. You know what I'm going to do? I'm going to substitute some values to have a look. So how could I do that? So we're thinking that, I'm going to just actually move this down. Let's substitute values to see if we're right. So we think the curve should go like this at x is 3. Let's have a look. When x is 1, what do you get? I'm going to do a little table of values, but you wouldn't normally have to, but I want to. Actually, what about when x is 0? What do you get? -2? I'm going to put the 7 up here somewhere. What about when x is 1? What have we got? 2 minus 9, that's -7, plus 12, which is 5, minus 2, that's 3. I've got the 0.13 approximately. When x is 2, what have I got? So we're going, when x is 2. Did I make a mistake with that one? Is it 13? 2 plus 12 is 14 minus 11. That's right, 3. When x is 2, what have we got? Maybe this -2 should be a bit higher. Come on, when x is 2. 2 times 8. 16 minus 36, that's -20. Plus 24, that's 4. Minus 2. Oh, this curve does a bit of stuff. Okay, yeah, so, sorry, probably not the best strategy to use. But at 3, we know it's 7. But look, it looks like the curve's going up and down a bit. And it is, it's a cubic. It's going up and down a bit. So I really think that it's sort of going, oh, I don't know, it might go like this. So I've got 1, 3, and I've got 2, 2. And I've got 3, 7. All right, so what we'd have to do, actually it's not a bad, it's a good question. I think that there's going to be a minimum somewhere here. We'd have to put first derivative equal to 0. If you want, let's do it. Let's sketch this curve. This brings us on to our next bit. We're actually going to sketch the curve. But this curve, this question's not asking me to sketch the curve. It's just saying how does the curve look like there. So what I'm going to do now, I think we've got another maximum and another minimum. You know how we learnt in extension 1 that this is this shape? That's how I'm thinking it's like that. But what I'm going to do, I'm going to get another piece of paper and we're going to sketch it using all the tools that we've learnt. So now what we're going to do, we are going to sketch function of x or y equals 2x cubed minus 9x squared plus 12x minus 2. Okay, so we're going to follow these showing any stationary points and inflection and points of inflection. So, and you've got to determine their nature of the stationary points. So that's what it'll say. So sketch it showing any stationary points. You have to determine their nature and show any points of inflection. We want to sketch it, all right? All right, let's start. Hold on, move this up. Ready? We got our function of x first. Now, this is going to take 2 pages. More than likely. I just hope I'm going to get some nice values here. First derivative we already did before, which was 6x squared minus 18x plus 12. Okay, I'm not going to do the second derivative yet. Remember we were doing this in exercise 2.2. We'd do this, we'd write the first derivative. What would we write next? Stationary points when f dashed x equals 0. So we put that equal to 0. So this is the same as what we were doing before. And we solve this. Now, what do you think? Divide by 6 first. Yep. Factorize. I think it's x minus 2, x minus 1. Oh, we were right. So therefore x is 2 and 1. Now, so this is the same as what we did before, but what we did before was now do up a table of values before and work out what the gradient did on either side. We're not doing that anymore. We're not doing that anymore. That's one method. We're looking at the second method. We know we've definitely got a stationary point when x is 2 and when x is 1. So there is only 2 stationary points. So let's just work out their y values. When x is 2, I think we worked out that the function of x, we worked it out, was also 2 times 8 minus 9 times 4 plus 12 times 2 minus 2. I think I got 2. And when x was 1, we already worked out that the function of x is 2 times 1 minus 9 times 1 plus 12 times 1 minus 2, which is 3. So we know that we've got a stationary point at the point 2, 2 and the point 1, 3. But now we have to determine their nature. So what we do to determine their nature is find the second derivative. So we now f double dashed x equals, you do the second derivative from the first, and you get 12x minus 18. And all you do now is substitute in your x values. Then we say, when x is 2, the second derivative is 12 times 2 minus 18, which is 24 minus 18, which is 6, which is greater than 0. And then we will put it equal to 0 and solve. Then you can find the points. Then we find the points. Then, next bit, do the second derivative and substitute in your x values, because you know you want to see what's happening with the second derivative when x is 2. Now when x is 2, second derivative greater than 0, so you write concave up and you draw it, and then you say therefore, because you draw it, you can see it's a minimum at 2, 2, because I already know when x is 2, y is 2. So we do the second derivative, then we substitute in our x values. Then we know we've got another stationary point at x is 1. See, the second derivative lets you work out the nature of the stationary points by substitution. When x is 1, the second derivative is 12 times 1 minus 18, which is negative 6, which is less than 0. That means concave down. So you draw it, and you can see, therefore, you've got a maximum at the point 1, 3, which is pretty much, I think, what I drew before. Now, we're going to look for inflections. Let me draw what we've got so far. Actually, you shouldn't put all the markings unless it's, really to scale. So what we've got is, I'm just going to put 7 up there. So let's sketch what I've got so far. This is what I know. I've got a minimum at 2, 2. So about there, I'd say. A minimum. I've got a maximum at 1, 3. I'd say it's about there. If you look up at the curve, I'll just write what the curve is here. Or you can see it on your sheet. It's 2x cubed minus 9x squared plus 12x minus 2. I know that the y-intercept is negative 2. So we got the maximum here, 1, 3. We've got the minimum there, 2, 2. And I knew that when x is 3, y is 7 from, earlier in the question. I'm doing the same thing. I'm missing something. Concave, look, concave down. Oh, all of a sudden concave up. What is lying in between? There's got to be an inflection. There's always an inflection between a maximum and a minimum. So how do we find inflections? You put the second derivative equal to 0. So, actually, I think this is in the next exercise, but we'll just do it now. To find inflections, we put second derivative equal to 0 and solve. So let's do that. The second derivative is 12x minus 18. Put that equal to 0. We get x is 1.5, amazingly. So where the pink bit is, you've got just an inflection, an ordinary one at 1.5, comma, and you can just wait. I haven't finished. Has anyone worked it out? All right, so wait, I'm not finished yet. When x is 1.5, function of x, someone's worked it out, is 2.5. Now, remember in the notes it said for for inflections there must be a concavity change. So you must do your little table with the second derivative, not the first derivative. We know that at 1.5, the second derivative is 0. So what you do, you just try a point on either side. You can't go too far because you're going to hit the stationary point. So I would just go 1.4 and 1.6. You can tell this is the second derivative. If I put 1.4 times 12 minus 18, that should be negative. You should get a negative answer. And if you do 1.6 times 12 minus 18, can someone do it? You should get a positive answer. Has anyone done them? Look, I know I'm going to get a negative answer because it's concave down there and here it's concave up after the 1.5. Look, we're going to be doing this for the rest of the topic now. Guys, has anyone done 12 times? So this is the second derivative. So if you put 1.4 into that, 12 times 1.4, please, someone help me. No, it's not. 12 times 1.4 minus 18. I need an answer. Negative what? And 1.6 times 12 minus 18. Positive 1.2. Can you see the concavity changes? The second derivative is going from negative to 0 to positive. You need to see the negative positive change. So concavity changes, you must do this table. If you don't do the table, you don't get the marks. Because point of inflection means second derivative is 0 and concavity changes. Therefore, we have a point of inflection at 1.5, 2.5. And there's your curve. No, it's not. Look. It would only be horizontal if the first derivative was 0 as well.